I'm going to attempt to teach this via Zoom. And let's see, I'm sharing the screen right now, right? Starting to get more people that are missing class because of COVID. So I'm going to attempt to teach this / record it at the same time with Zoom. So I just want to do kind of a last 6.2 example. Because the homework assignment was tricky in the sense that they asked some pretty thought-provoking questions, and sometimes you had to add a lot of stuff together. But I just want to make sure that with respect to what I want you to understand, and if I ask the question a little more straightforward, that you get it. So one last kind of shot at making sense of that. Let's see. So let's say I have let's say I have 6 kids. Thank God I do not have 6 kids. And because of the family that I live in, let's say that I have a a 19 or 19.19 or 19% chance of, let's see, what's some kind of a high cholesterol. So let's say in my family, there's a 19% chance of having high cholesterol, and I have 6 kids. And so you can fill in some other birth defect or something like that. Maybe Down syndrome, like if there's 19% chance in my family of having Down syndrome and I have six kids, then it'd be kind of like, what's the whether my kids might get a birth defect. And so how's that really work? And so the power of a probability, a binomial probability distribution, binomial because they either have high cholesterol or they don't. That's why it's binomial. There's only 2 options. They either have it or they don't. Or I could say today, hey, there's a 19% chance of rain. It either rains today or it doesn't rain. There's only two possibilities. But all you need is those 2 things, an n, like a fixed number of kids that you have, or a fixed number of days in the week, or a fixed number of days in the month, or something like that, and a percent that something is going to happen, and then you can make a probability distribution. So if I let X be the number of kids that have this birth defect or high cholesterol, I'll say HC for high cholesterol, the number of kids that have high cholesterol, then I could have no kids that have high cholesterol, or 1, or 2, or 3, or 4, or 5, or 6. What made your assignment kind of hard is it wasn't that small. On a test, I'm going to keep it nice and small like this. N's not going to be 36, 38, 52. It's going to be something nice and small. If that's the case, then I just have 7 probabilities to figure out, and I can do it relatively quickly. So you have 2 methods for this. And let's see, I'm going to start kind of in the middle of the list here. So does this logic make sense? And you should be staring at your note sheet for this, especially as we're getting ready for a test. I'm staring at this formula right here and saying, okay, what do I do with that? So I'm going to show you both ways really quickly. So NCX, well, for me, N is 6 because I have 6 kids, and X is, well, which probability am I working on? Right now I'm saying, what's the probability that 3 of my kids will have high cholesterol? So that's my particular X. So for me to get this, I have to say 6C3, because remember, my 6 kids have names, and so which kids ended up with high cholesterol. I care about which kids are which. There's lots of ways that can happen. And then I say, well, the probability of them getting high cholesterol is 19%, and 3 of them had that. So that's this part of the formula, the probability raised to the x, but then I also have to multiply by the other probability. Remember, Q is the complement of that event. In other words, if the percent they get cholesterol is 19%, then does it make sense Q is the probability that they don't get that? If there's a 20% chance of rain, it means automatically there's an 80% chance that it won't rain. If 19% of my kids are likely to have high cholesterol, then automatically one minus that probability is going to give me the Q probability. So automatically, this would be 81%. And if 3 of them had this condition, then that means the other 3 automatically would have something else. So for 2, it would be 6C2. There'd be 2 kids that had high cholesterol, and then automatically 4 kids that did not. So a total of 6 kids. Like that's what I'm typing into my calculator. So be able to do this. So I'm using a more normal calculator that most of you would have. So 6, and then I go over to math, find probability, 6C3 times 0.19 raised to the third times 0.81 also raised to the third. There's that probability. So I got 0.7290. So to 4 decimal places, that would be 0.729. 0.729. I was going to say 729. That's a huge number. 0.0729. Now, one of my concerns about this is not just making this table, but interpreting it. Like, do you understand what that percentage means right there? Yeah, I just got 7%. What does that mean to me as a parent? That means I have a 7% chance that 3 of my kids are going to have high cholesterol. That's what it means. And again, automatically, that means 3 won't get high cholesterol. I have a 7% chance of that happening. So that feels good. Like, oh, that's pretty low. Is that unusually low? If this happened, should I be surprised? Like, these are all questions you should have a sense of. Remember, plus or minus 2 standard deviations was 95%. And so that's usual. So therefore 5% is unusual. This is bigger than 5%. That's not unusual. So if that happened, I shouldn't be surprised. Now it's close to 5%, but I'm not surprised that that's happening. So on the test, you got to be able to make a probability distribution and interpret it. So by hand, that's kind of the long way. The cool thing is you're actually seeing the probabilities in front of you. The cool shortcut, Binom PDF, is the same thing. It returns the probability of an event. Isn't that what I just got? Is the probability that 3 of my kids. And again, what's cool about this is I'm predicting the future. I'm not reporting what happened. I'm actually predicting what's going to happen in the future. That's why this is so powerful. So I could do this way faster, although I probably wouldn't have any idea what I was doing by just typing Binom PDF. And then notice the syntax here. First N, 6, second P, 0.19, and then last X, which for this particular probability, it was 3. So where do I find that? Well, it's behind the distribution button. So second distribution, I want Binom PDF. I want the individual probability. So I hit that. This calculator is kind of fancy because it's reminding me. So I can say, oh, there's 6 trials, N is 6. My probability of getting high cholesterol was 19%. And the individual the problem I'm working on right now is what happens, what's the probability for 3? And so notice the syntax here. See how it typed it in for me? So in a sense, if you have my calculator, the 84, you did not need to know this syntax right here. But notice it put N first and then P second and then that third. And notice I got the same answer I just got a second ago. That's pretty fast, right? That's kind of cool. Does anybody have that, the 80, just the 83? But that's what you get from the library most of the time. Yeah, yours looks like mine, right?
Yeah.
Now, what's really cool about this one is, what do I have to do to get all these other answers to make the entire table? I just need to do that again, except for just replace the 3 with other numbers, right? So how do I make that happen? Right above enter, it says entry. So you hit second and then enter, it retypes it. And then you just go back and say, okay, what's the probability of 0? 0.2824. Second entry. This is what you probably would want to do on the test. Be careful with this one. Maybe you missed questions on the homework assignment. If that's rounded to 4 decimal places, what should that be? 0.397, what? 5. And what about when that's 2? 0.2331. Again, you got to round that up. And what about when that's 4? Notice that's the first one that was unusual, 0.0128. If I ended up with 4 kids with high cholesterol, if 19% of people in my family had high cholesterol, I ended up with 4 kids that had it, that's a really low chance to happen. And so that's kind of strange. That's unusual. That shouldn't have happened, if you will. That was not predicted. That's crazy. That would only happen 1 in 100 times. And I only had, my 6 kids one time. And so unfortunately I got the 1 in 100. That's unusual. And because 19% is such a low number, these are just going to continue to get less and less likely. You notice it's down to 0.0012, and every single kid that I have all has high cholesterol. It jumps into scientific notation. If I move the decimal point 4 places to the left, like don't screw this up. No, it says 5, doesn't it? So it's 4.7. I throw a bunch of zeros out here. I don't even know how many to throw out there. And I move 1, 2, 3, 4, 5 places to the left. What does that round to 4 decimal places? That 4 means this stays at 0. So it's actually 0. Again, rather than writing 0 there, it's better to say, better than saying this, because that literally is 0. It's better to say 0 plus there, just because you're telling somebody it's effectively 0, but of course there is a chance. What is the chance? 1, 2, tens, hundreds, thousands, 10,000s, 100,000s. There's 5 in 100,000 chance that all of my kids would have high cholesterol. So if that happens, it feels like something's wrong here. I gave them the wrong food. I don't know, something went weird. If you can make that distribution using one of those 2 methods, I don't care which one, leaning on the note sheet, because it's easy to kind of forget this stuff, then you're in a position to answer all the questions. So they ask some tricky questions in the homework, which is great. That's fine for the homework, but I'm not going to ask quite as tricky questions on the test. Again, the easy questions are just, what's the probability of having 4 kids with high cholesterol? And you just say, oh, there it is, 0.0128. That's the easy question. And frankly, if that's the only question you were asked, then you didn't necessarily make the whole table. Does that make sense? You just need to make that one answer and you're done. But as I said before, the real question, the real life versions of this are seldom asking just for one probability. Usually it's something more like this. What's the probability of having more than 4 with high cholesterol? Again, that's easy as long as you can interpret the question, and that's not simple. You got to think about that a little bit. But this time, you're just adding up a bunch of probabilities. Notice there's only 7 of them here. You don't need to, put this in Excel. You don't need any fancy buttons. Just type it in. But what does it mean to be more than 4? Which probabilities are you adding? Just 5 and 6. Notice I didn't say 4 or more. That means 4 got included. I said more than 4. So I'm adding the probability of 5 plus the probability of 6. But interestingly, 6 does nothing anyway. So it's kind of like really all it is just 5's probability, right? Or I could say, what's the probability of 3 or less or something like that. So if you can make this distribution and then answer straightforward types of questions from it, that's all you need for the test. Now, again, there's lots of tricky questions in the homework assignment that would have made you think harder. And they're actually good questions because they're very realistic, but I find myself having to read those kind of questions more than once to kind of make sense of them. And there were questions in there where they didn't automatically tell you a percentage like this. The one about the men and women getting hired for a job, like there was no percentage there, but they said that there's an equal chance that a man and woman would be hired. Well, that's a tricky way of telling you it's 50-50. In other words, you have a 50% chance of getting hired. So rather than just saying that in nice plain English, they put it into words, which made that really hard. And so you should have found that a very difficult assignment. Again, I sent an email to you guys on Saturday, and I hung out with 6 or 7 of you on Sunday over the weekend to kind of help with some of those questions. I'm going to try to do that when I can, especially when some of the sections are harder if I'm around on Sundays. I'll try to not do it last minute if I can kind of see this is a hard section and I know I'm going to be home Sunday evening or something like that before your homework is due. Just give you a chance to talk and ask questions and think these things through. If you can do that, what we just did right there, that's half the test. The other half is chapter 7, which we're going to start today. But let's talk just a little bit more about this that I think is cool. Other things you should be able to do after making this, you should be able to answer this question. What's the mean? You should be able to calculate it. And you should also understand what you just calculated. So for a binomial probability distribution, you don't have to add up every single x times every single probability. You just got a cool formula here. 6.2. N times P. And this should make some sense to you. So for us, N was 6, P was 0.19. If I punch that in, 6 times 0.19, I get 1.14. I'm going to call it 1.1 since, again, you should be rounding to one more decimal place than your data. This was very important for today, but this was discrete data. You can't have 1.2 kids have high cholesterol. You can only have 1 or 2 or 3. Discrete, got to be whole numbers. So therefore, carrying this out one more decimal place makes sense. But I'm gonna pick on you a little bit. I want you to think about this, but I'm gonna pick on some people. I'm gonna ask you, what does that mean? Like, great, you got 1.1. And as a teacher, a lot of times, if I ask that question on a test, I might write next to it, good job. But my point is, if you don't know what you just calculated, if you don't understand what that number is, then this does not do you one bit of good in the real world. You understand that? I want you to be able to calculate that, but you got to understand, like, why would you even want to calculate that? What is that even for? I don't care if you're wrong, but like, take a stab at it. Kristen, what do you think? I got 1.1. What does that tell me about this scenario? And I don't know as a financer, or I'll guess, but I really don't feel very good about it because I'm going to pick on more than just Kristen. Nice and loud. Said average is like 1%, but tone of voice is like, I don't really feel very good about it. Is that true? What do you think, Danny?
I said the mean is 1%, but on average, you're gonna have those outcomes being a little bit above 1.
So you use the average, use the idea that this would be the average. Samantha, what do you think? You guys are all knocking on the door, and what Samantha said is pretty much bang on. In other words, if I have 19% of people in my family that have high cholesterol and I have 6 kids, this is what's likely to happen to me. I'll have 1 kid then that has high cholesterol. That's what mean is the expected value. So all 3 of you guys were actually kind of hitting around that. So that's what I would think would happen. Now, why is it, if you look up at the probability distribution, what do you notice about the biggest percentage up there? Is it the biggest percentage, the most likely thing to happen? If you were betting and saying, what do you think is going to happen? Is it the highest percentage is 1. You see how that agrees with this? The highest percentage is where you would bet. However, notice although that percentage is about 40%, if I said, do you think that I'll have 1 kid that has high cholesterol or something else? Notice if for 1 kid it was 40%, well then isn't something else 60%? So actually it's more likely that something else will happen. But if you actually had to bet on it, the answer is going to be 1. This agrees with that. This says 1, and so does the highest percent over there. You see what I'm saying? So again, what's so cool about this and what's so powerful is we are predicting the future. Does that make sense? Like in my family, there's 19% of people that have high cholesterol. And so if I decide to have 6 kids, then I can prepare for one of my kids having high cholesterol. Now, does that mean that's what's going to happen? No, because as I said, is it 60% somewhere else? So would it be weird if I had 2 kids that had high cholesterol? Well, notice that's a 23% chance, so that's not weird, that's not unusual. Would it be weird if I had 3 kids that had high cholesterol? Again, that's not unusual either, because that's 7%. Now, if I had 4, that would be unusual. You see what I'm saying? Like, that's why this is so powerful. We're not reporting on the fact that I had my 6 kids like 10 years ago and what happened. We're not reporting on it. We're figuring out what's going to happen in the future and preparing accordingly. What if this wasn't high cholesterol, but it was something like Down syndrome or something a little tougher? Like you gotta take care of your child in a totally different way. School's going to be way different. And so, should I have 6 kids? How should I prepare? I mean, it's pretty likely we're going to have 1 child that has Down syndrome if 19% of people in my family have Down syndrome. And so it's like, okay, let's get prepared. Now, might I have none? 28%. I might. If that happens, of course, since we're talking about something negative, it's like, okay, good deal. That's great. We got kind of lucky. You understand why mean is powerful then? That's why you calculate it, because you're trying to figure out what's going to happen. And this is kind of your best guess. Question?
How can you tell if it's unusual?
Yeah, so unusual is if that percentage is less than 5%, that's unusual. Now, you had a question in your assignment where they assigned a tighter number to that, because they were saying, based on women getting hired, they said, would it be, what's the percent chance of us hiring, not very many women, so to speak? The idea, is that just something unusual that happened? So again, in this case, if I say I had 4 kids, well, I would have thought I would have 1. But based on this percentage right here, is that actually unusual? Yeah, that's less than 5%. But what 3? No, that's not. So although in a sense, if it was something negative, I might say, bummer, there's 3. It's kind of like, well, that wasn't that weird. That could happen. So, again, if I was a parent, I would think, let's prepare for that. Let's prepare to have 3, because that could happen. And if it's less, then okay, I got prepared, but I didn't need to be prepared. And so, okay, that's all right.
Is the 5% part of this problem, or is that general?
As a rule of thumb. And that's because of the empirical rule. We said 95% of the time you're within 2 standard deviations. And so we said that's normal. So 95%, that's where 5% came from. Because if 95% is normal, then at least 5% outside of that. Now,
one more question
yeah, go ahead.
the at least thing,
Yeah.
because I know at least could be anything, like that number than anything above that or whatever, but on the homework, when it's at least 1, there's that rule where you can do the probability of 0 times and then 1 minus that or whatever,
Yeah.
so 0 minus 1 or whatever, but
Good for you.
can you use that with other numbers, or is there no, because I tried that with some of the larger numbers, like 19 or something, and it didn't work.
Yeah, and I would certainly, any problems you have with your homework, I would love at some point to look with you one-on-one, because it could be a profound mistake, like you have no idea what's going on, you're totally screwing it up, right? And then we talk about that, but it could also be just something tiny, like a rounding error. You know, I mean, if the right answer to this is 0.0728 and you just rounded it wrong, in my open math, it just looks like it's wrong, but is that profoundly wrong? No, that's pretty much right. So, you know, I want to help you get to the bottom of those kind of things. So to Jade's question, if I said, what's the probability that one or more of my kids will have high cholesterol? One or more means add all of these together. There's only 6, 7 of them, so just add them. But what she's saying is, could you just go 1 minus that not happening, 0.2824? Yep. Do you see how that would be the answer to 1 plus 2 plus 3 plus 4 plus 5 plus 6? That saved me a bunch of time. Now, if I actually add those together, will I actually get this exact same answer? It could be off. It could be 0.7175 because of rounding. Because did you notice some of these, like I think it was this one, that 5 went up from a 4 to a 5, for instance, like that got rounded up a hair. Could that actually cause your final answer here to be off by a little? Yeah. Now, my open math would care about that, and that would be frustrating. I'm not going to care at all on the test, right? Like, close enough, you got it.
Can we do it like when it's like at least something, because is it always gonna be 1 minus the 0, or is it?
Yeah, so what if I said at least 2? What's the probability that I have at least 2 kids that have high cholesterol? Well, at least 2 includes 2. So here's my 2 choices. I could say 0.2331 plus 0.0729 plus 0.0128 plus 0.0012. Again, I could easily have just typed something in wrong, so I'm kind of staring at that really quick. And so there's the answer, 32% chance that I'll have at least 2 kids that have high cholesterol. And again, now I can answer questions like, would that be unusual? No, that's 32%. It's not 5%. That wouldn't be unusual. What else could I have done? I could have said 1 minus these 2. So I could have said 0.2824 plus 0.3975, and I could have went 1 minus that number. Notice I didn't quite get the same answer. Isn't that interesting? They were indeed off by 0.0001. This, when I did it this way, I got 0.3200. When I did it this way, I got 0.3201. If I'm in my open math, because it's a computer, it might mark one of those wrong. And I'm, you know, then I'm thinking, oh no, I don't know what I'm doing. Well, maybe I do. It's just kind of a rounding issue. That's why I said at the start of this term, like, email me those questions, because I want to either just give you credit for it because it's just a rounding error, or, you know, maybe there's something wrong with the problem and I need to fix that for future students. So for the test, make the chart, answer a few questions about expectations. One more quick calculation. So we found the mean. Can you also find the standard deviation? And that's the whole point of this. Although I would expect to have one kid that had high cholesterol, this chart here, this probability distribution is clearly saying that that's probably not going to happen. Probably something else is going to happen. Actually, there's a 60% chance that something else is going to happen. And that's why standard deviation is so cool. There is variation here. So you're looking at your note sheet, again, leaning on this note sheet. Probability, binomial probability distribution. Square root of n times p times q. So for us, that's the square root of n, which is 6, times p, which is 0.9, times that q that we used up there, 0.81. So my calculator knows the order of operations, so I can just type all this in. Square root of 6 times 0.19 times 0.81. I'm told 0.96. Or again, if I round to 1 decimal place, oddly, that would actually go up to exactly 1, like 1.0. So again, I want to pick on some people. What does that mean? Amanda, what does that mean? What does that tell me about this situation? It's got a standard deviation of 1.
That is one away from the mean.
That's exactly right. It's very important to understand that that 1 is 1 away from the mean. It's not just 1, it's 1 away from the mean. Lucas, what do you think? You got anything to that? Yep, what does that mean? There's nothing wrong with that answer. Until, at least as long as you fix that before the test. Zach, what do you think? Say that one more time, a little louder. Yeah, see, when I have the mean and the standard deviation, then that allows me to be more specific about what kind of I would expect to get 1, but would it be weird? Would it be weird to be either 1.1 plus 1 or 1.1 minus 1? Is that weird to vary by 1 standard deviation? No, that's what standard deviation is typical deviation. So notice this is plus or minus 1, mean plus or minus 1 standard deviation. So I got 2.1 and just 0.1. And so this is saying it would be perfectly typical. Frankly, 0.1 is kind of like 0. I mean, it's pretty much between 0 and 2. So it would be very not surprising if I ended up with 0, 1, or 2. And again, isn't that what these percentages are saying up here? Yeah, I would expect this, but notice the next huge percentages are on either side of that. So it wouldn't be weird at all if I was here and those percentages agree with that, right? 23%, you're not surprised if that happens. 28%, you're not surprised if that happens. So that's super typical to end up in here. Notice that comprises, well, if this was a normal distribution, that would be 68% of the time. Now, is this 68%? Not necessarily. Maybe this isn't a normal distribution, but that's the idea behind 1 plus or minus 1 standard deviations. Would you agree that plus or minus 2 standard deviations is important too? Because that's what we've been talking about something being usual or typical. If I take 1.1 plus 2 of these, I end up with 3.1. If I take 1.1 minus 2 of those, I actually end up with negative 0.9. Notice that's impossible. Like that's in a sense, you can't go below 0. But this is basically saying exactly what we said before, which is why I'm showing you this. Would it be weird to be somewhere between 0 and 3 kids that end up with high cholesterol? The answer is no. That's normal, plus or minus 2 standard deviations. Didn't we just say that a second ago? To have 3, is that abnormal? No, 7%. Now, is it close? Is it close to being abnormal? Yeah. Is 3 close to being abnormally high? Yeah. If we make it to 4, then it's going to be abnormal or unusual. So again, if I'm a parent and high cholesterol mattered or something like something I would needed to do about it, I'd be preparing for 0 to 3 kids that had that, whatever preparing meant. And if it was outside of that, I'd be like, oh man, I'm one of those unusual people. That's the takeaway. Like that's the test question right there. Just find the whole thing, do everything, find the mean, standard deviation, explain what it means in that context. If you can do that, you're useful to somebody. Like you can get paid to know this. If you're just sticking numbers in formulas and you have no idea what you just found, this really isn't doing you much good. So I think of the difference between an A and a B. If you can punch stuff in and get the right answers, that's a B, you know, you get yourself out of here. But to actually, you know, get an A, it kind of means you got to understand what you just figured out. I mean, this is pretty powerful. This is predictive, preparatory. What do you think? Anything else you want to ask me about that? I just want to make sure, because I think that assignment was tricky, that you kind of say, okay, well, you know, as far as the test, this isn't going to be quite that bad. Okay. So fortunately today, we are, in one sense, not doing something totally different. I'm going to teach you some new things, but we have been talking about normal distributions the whole time. As a matter of fact, I was just talking about it a second ago. When we say plus or minus 2 standard deviations is 95% of people, that's the normal distribution, the empirical rule that's on your last assignment. And that's all this section is really about. Does it make sense here in this, what we just did a second ago, that the data is, for binomial distributions, the data is discrete, meaning how many of your kids had high cholesterol, not 1.7. Today is really just saying, well, what if the data is continuous? What if there is decimals? Can you still kind of have this predictive value? The big takeaway from that section is being able to make this distribution right here so that you can kind of help people prepare. Now, keep in mind, I was talking about me just preparing for my own kids. But again, think about this. If you're a doctor and you have patients coming in, this means 28% of your patients will be in this category. And if you have like, you know, 1,350 patients, like that's a lot of people. And, you know, so if I need to have medication on hand, that'd be kind of cool that you could actually prepare for that ahead of time. You see what I'm saying? And I could prepare for 39%, roughly 40% of my patients being like this and 23% like that. And, you know, this is really unusual, but maybe that takes a really crazy medication. And so I say, okay, well, that's pretty unlikely. But I have 1,352 patients. Guess what? 17 of them are going to have that. Although that's unusual, does that mean nobody ever gets it? No, if I have that many patients, 17 of them will have it. Wouldn't it be cool if you actually had that medication on hand? If each one of them needed it and you prepared for 17 of them to have that, even though that's unusual. Do you see how predictive and powerful this is? Do you see the concept? But that's discrete. What if your data is continuous? We're going to do the same thing. We just need to come up with a bunch of percentages. But this is for continuous data. Okay, so let me show you what I mean. I don't see it. Make sure I'm not forgetting anything important. So I just want to show you how something works that you already understand. So you agree from before, if I take the mean plus or minus 1 standard deviation, we said that was approximately 68%. Now, where did that 68% come from? The book and me told you that was the case, and you said, oh, you just believed me, right? You didn't kind of have a reason for that. You just said, oh, okay, thanks. That's cool to know. I didn't know that. Must be true. You're probably not lying to me. But what I want you to understand is on the normal distribution that you already know about, the one that I printed off on your last note sheet, looks something like this. Centered at 0. Here's 1 and here's -1. What you do need to understand today, though, is remember those are z-scores. Like those are Z's. That one standard deviation, that's what one standard deviation is a Z-score of 1. That's what a Z-score is. So I asked you questions on the last test, something like if your kid came in weight-wise when they were born with a Z-score of -1.9, that's all you should need to know to tell them something about their kid. If their Z-score for weight when they were born was -1.9, you should say, oh, negative, huh? That's below weight. They're below average. Are they unusually below? If their Z-score is -1.9? No, because it's not quite 2, but they're close, right? So as a doctor, you should say, you're low, but that's still normally low, but it's kind of close to not being normal. So we're gonna, watch this at our next appointment, that kind of a thing. You should understand. So we've already done this. So these are both Z-scores. And so literally that area right there is approximately 0.68. Like that's the same percentages that we just saw sitting over here a second ago. They're just percentages. So that's an area, but that's also a proportion of people, a proportion of your patients, if you will, or it's a percentage, or it's even a probability. So the next person that comes in, 68% chance they're going to be in that range somewhere. It's the same probabilities we just figured out a while ago. It's just that in this case, we can have decimals. Now, what I want to show you something kind of cool right now is where did these come from? So on your note sheet, normal distribution, this is 7.1 and 7.2. Let's look at this one right here. So I'm going to show you how to, well, just a second ago, we used binomial probability distribution function to get all those percentages. I'm just going to use the same thing, but this time normal. Notice the syntax is lower limit, comma, upper limit, comma, mean, comma, standard deviation. So it's like I got to type 4 things in there. So I'm just going to go get that. Now, in the example that I just pointed out, what's our lower limit? -1. What's our upper limit? +1. In other words, that's the percentage or the probability that I'm after, is what percentage or probability do I have of landing inside here with my kid being born? Where is that function in your calculator? Well, it's the same place that we just were a minute ago. It's in distributions, right above variables. So second distributions. And the top menu right there that we've been skipping over, that's the one we're looking at now. Notice that note sheet says normal CDF, cumulative. In other words, I'm going to add a bunch of them up. I don't want just one probability. I want all of them. And so just notice that here. I'm saying normal CDF. Notice there isn't even a normal PDF on here. We don't really have a reason to do that. So in my calculator, if I arrow down to that and I say, what's my lower limit? I say -1. What's my upper limit? +1. Again, those are Z-scores that I'm typing in there. And if I leave the mean at 0 and the standard deviation at 1, which is again what your chart did in the last section, and I'm going to add something to this note. I left a space here because really what we're studying today is a standard normal distribution, and that standard is sort of code for the mean is 0 and the standard deviation is 1. So if you type that in and hit enter, what does it say? So I have everything in I'm supposed to have in. Again, the cool thing about this calculator is I don't need to know this syntax here. Lower limit goes first, upper limit goes second, then mean, then standard deviation. If you have an 83, you actually have to know that order. In mine, and it looks like in yours, I just type all of those things in, and then when I say paste, it puts them in there for me in the right order that my note sheet says. So there's my lower z-score, there's my upper z-score, there's my mean, there's my standard deviation. So it's not requiring me to memorize that syntax or the order. But notice when I hit enter, it says, hey, there's where that 68% came from that I've been telling you. So a couple of things. One thing is, I'm almost sure I know why yours said error. It definitely distinguishes between a minus sign and a negative sign. If you hit -1, it doesn't understand that. It sees that as like if I said 6 minus 1, oh, that's 5. But if you said there isn't anything -1, it's like, I don't know how to do that. What do you mean there's no number -1? It sees that as an operation. So it could be that. Make sure that's a negative. So again, I'm not showing you the math behind this. I might show you before today's over, but that's where the percentage came from that was on your last note sheet about ±1 standard deviation and ±2, the empirical rule. That's where that came from.
What does PDF tell you instead of CGI?
PDF tells you a single probability. And in this case, we're looking for a range of probabilities. So it's really unusual in this to have a single probability in this world of continuous numbers. So again, if I had a kid and they were born, does it make sense they're not born 1 pound or 2 pounds or 3 pounds or 4 pounds? They're born 1.27 or 3.86 and weights like that. And so to say, what's the probability of your kid being 3.86 pounds? That's what that button would be for. But the problem is like that's rounded off. So if you wanted to know what's the probability my kid was born 5 pounds, you'd have to use that button. But anyway, don't use it, leave it at that. So watch this. If you go second enter to retype it, you should know the answer to this. What if I'm between 2 and -2? Wasn't that the 95 something percent? Yeah, that's where that came from. It's actually 95.4. Notice it's way more accurate than what you knew. If somebody wanted to know, it's actually 95.45% apparently. So what is this section about? It's about the fact that we don't have to just be stuck at 1 and 2 now. You can actually go any place you want. That's what this section's about. Okay, so there's 2 things you need to know today. One of them is if you're going from a z-score to a percent, remember that percent could be a proportion of people or even a probability. What's the probability the next person comes in, they have a certain sickness or whatever? Percent, proportion, probability, they all say the same thing. And you might have homework assignment questions in my open math where they say, what proportion of people, what probability is a person? And you need to see those as like, oh, that's the same question. What percent of people have this sickness or whatever? That is done with the normal CDF function. So let's just look at a few examples. This is why you have this sheet, because I wanted you to be able to draw this. So I have some nice looking, this isn't just an ugly sketch, this is kind of a nice drawing. And so now let's use this in just a slightly more powerful way. As I said, what's important here is just the fact that we're not stuck between just -1 and 1. We can go between anywhere. And you may remember on a previous assignment, on a homework assignment, they even asked questions like, what percent of people are between -1 and +2? And you had to kind of look at that empirical rule and kind of figure out all these little percentages yourself. Well, now we don't have to do this anymore. You can just go between any 2 z-scores you want and find any area you want. So for instance, let's do this. What if I said what's the probability that you had a z-score that was between 1.8 and negative 0.4? Now, would you agree that, again, that's normal? This is not outside of +2 or below -2, so this is typical. But what percent of people are between those z-scores, or what proportion of people are between these scores, or what's the probability the next person that walks into my office, if I'm a doctor, is going to have a z-score for some health number that's between those two values? Well, I don't have to have this memorized. I just go to the normal CDF button and put in -0.4 for my lower limit. But the reason I gave you these pictures is make sure you kind of can graph this. In other words, what are we talking about? Well, notice if this is 0 and this is -2, then that means this is -1. And so this would be -0.5. So -0.4 would be about right there. Do you agree? And then 1.8, well, if this is 1 and this is 1.5, then wouldn't 1.8 be about right there? And so I'm literally talking about what is that area right there. Again, it's important to understand that the area under the curve is always equal to 100% or 1. Again, is that new? No, wasn't all of these areas right here, all these areas added up, wasn't that always 1 in 6.2? If you look at every possibility that happens, isn't that 100%? Well, is this any different? No. The same exact thing. It's just that if you made a bar graph of this, you would have 7 bars on it. Well, because now we have continuous data, there's like infinitely many bars here touching each other. So it looks like a curve. But this is still just a picture of a bar graph. Now, I don't know about you, but drawing that out accurately, would you agree that, let's see, there's this little area missing out here, which looks smaller than this. If this area was equal to that, then I'd say this is 50%. That's 0.5. But to me, this looks bigger than that. So I'm guessing this is like 0.6. That is 60%. Now, am I right? No. But that's reasonable. You see what I'm saying? Again, I'm trying to spend some time, like, don't just push buttons and have no idea what you're doing. You might as well not be here. You got to reason about this a little bit. What percent of people fall between these two z-scores? What's the probability the next person that walks into my office is between those two z-scores? Based on that drawing, because this is a nice accurate graph, I'd say it's 60%, but let's just let the machine tell us. Second distributive, normal CDF, my lower limit, -0.4, my upper limit, +1.8. I leave the mean and the standard deviation at 0 and 1. It types it into the formula for me and says, hey, 62%. My guess wasn't that bad. Again, how do you write that down? 61.9%, 0.619, 0.6195 if you rounded it to 4 places. I don't care how you round it. As I said, I think the best way to write it is like that. Don't write it with percent signs because you have to do math with this. So again, if I'm that doctor with times 1,352 patients, I would say, oh, how that percentage right there of my patients, roughly 62%, what does that mean? That means 838 of my patients are going to be there. And maybe that's the ones I don't have to worry about, right? Like, oh, that's good. I don't have to worry about them. It's the other ones I got to worry about. So I'm usually doing math with that. So again, do you see that that's an area? It's a proportion. That's the proportion of my patients. It's a percentage of my patients. But it's even a probability or a prediction, which is its most powerful use. It's my hope that you don't see this as anything new. You already knew this, between 1 and -1, 2 and -2. All we're doing is saying, hey, it doesn't have to be right on a certain number. I can be any place I want. What about this? What if I say, what's the probability that somebody comes in with a z-score bigger than 2.1? Now, again, you should have a knee-jerk reaction to that, like, ooh, bigger than 2? You mean unusual, unusually high, as a matter of fact, right? This is not just unusual, it's unusually high because it's more than 2. So my next patient comes in, what's the probability that they're bigger than 2.1 and some health number or something like that? Well, again, can you draw a picture of that? What's the area? What's the shaded area that that's referring to? You have to physically draw a picture for this, or at least mentally. At some point, maybe you don't need to draw the pictures anymore, but for a long time, you probably do. So you should say, well, where is the z-score of 2.1? Remember, z-scores only work if 0 is the mean in the middle, that's the mean, and 1 is the standard deviation. Well, you should say, well, there's 2, and here's 2.5, so 2.1 would be about right there. And notice I said higher than that. I didn't say lower. When you draw that line, that doesn't mean you're done. I could have said lower, which means I'm shading this whole left side. But I didn't say lower, I said higher. So that means we're talking about this side. So I'm looking for that percent right there. So now again, you should have a reasonable answer to this. You should be able to reason out a decent answer before you even punch buttons in the calculator. Don't you already know that between here and here is 95%? So if that's the case, then what percent is left in the tails of this that's not counted for? Yeah, 5% total, but it'd have to be split here and here. And again, that's on the note sheet that you have before. From here, and notice this actually goes forever, just gets closer and closer and closer. This would be 2.5% or 0.025. But is that what we're doing? No, we're actually just a hair to the right of that. So that means our area is going to be just a little smaller than this. So maybe 0.02, I don't know. My point is I'm not just pushing buttons. I have a sense of this already from what we've already talked about. It's just that I don't have to guess. I can get it exactly right. Now, what's the problem with this one? Last time, this was my lower limit and this is my upper limit. But how do I do that here? I only have one number. Well, notice the shading. Is this the left or the right? I'm sorry, the upper or lower limit. Is that the upper limit or lower limit? That's the lower, but there isn't an upper. So what do I do there? So second normal CDF, lower limit 2.1. Remember, these are standard deviations. And we said we had one lab where you ended up with like somebody that has z-score of 4. Like 4 is a pretty high z-score. Just put some big number in there. So I'm gonna try 5. Just watch this though, don't do this. I'm gonna try 5. Notice that gave me exactly what I thought, which was something a little less than 0.025. Does that seem reasonable? Now, how did I know to go from 2.1 to 5? Why didn't I go 2.1 to 6? What do you notice? Danza, you had a comment or a question?
I was gonna say, because at that point, you're getting to like the E- number, whatever number is there, so it's not gonna have that big of an effect.
Yeah, there's so little area out here that it almost doesn't even matter. If I'm 5 standard deviations away or 6 standard deviations away, notice like they're almost the same number. Rounded to 4 places, those are the same exact answer, aren't they? So just to be careful, I mean, a person could say, I'll go out to 99, which is ridiculously high. But again, notice it's like almost the same answer. Is that any higher? Yeah. It's higher than this, but you have to get out to, what is that, 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places before it changed by one number. So sometimes when you're in the tails, you don't always have a top or a bottom end. It's missing. So you just put in some big number. I think your textbook makes this more complicated than it needs to be. It says, put in e to the 99 or, some gigantic number like a billion. We were already getting the right answer when I put 5 in there. You see what I'm saying? 5 standard deviations, a z-score of 5, that never happens. We said above 3 was an outlier, not unusual, an outlier. So what's 4 and 5 and 6? Like that just never happens. There's hardly any area out there. So I typed, just to have this in the notes, normal CDF. I put in 2.1 for my lower limit. I put in whatever 9 for my upper limit, 0 and 1, and I got 0.0179. If I rounded correctly to 4 decimal places, I got roughly 2%. As I said before, if you have 1,352 patients, that's still 24 humans. That's 24 humans on your list of patients. Although that seems like a low chance. If it's like, what's the chances my kid's going to have some debilitating disease? Whew, only 1.7%. Oh, good. That's probably not going to happen to me. But with 1,300 people, that's going to happen to some people. Quite a few, actually. That's a pretty big percent when you start stacking it up against even a town the size of 1,352, let alone like the whole country's population. Jade.
On the test, do you want us to use a certain higher upper limit or just make up or down?
No, I don't care. I'll probably say round to 3 decimal places, but if you had 0.0178 here, it's not like I'm going to go wrong. It's like I might say not rounded correctly, and then I'm going to sit there thinking, it's worth 5 points. Should I take one off? Probably not. It's probably what I'm going to think. You get the point. But that's why the book says use a ridiculously giant number. What about this? What if I say, what's the probability that you get a z-score less than -0.82? Again, you should see that as, below. You're lower than other people in cholesterol or number of kids that you have or eyesight, whatever. You're a little below other people. What area is that? Can you shade that region so you have a sense of what you're talking about here? Let's see, -0.82, where is that? This is -1, this is -0.5, it'd be like in here somewhere. Notice that was really accurate, like to the 100th place. What side of that am I shading? I said less than this time, so left, exactly right. Exactly correct. So now that you have it shaded, is -0.82 the lower limit or the upper limit? It's actually the upper limit. What's my lower limit? What am I going to put? What am I going to put over here for this number out here? This is -2, this is -3. Yeah, I put in -5, -8, -19, whatever, some biggish negative number. So normal CDF -10 is left, -0.82 is right, 0 and 1. Because this is a standard normal distribution. I didn't take time to reason this one out. I just started typing. I didn't think about it at all. And frankly, it just didn't occur to me to think about it. I got 0.2061. Does that look about right? Does that look like 20% of that curve is shaded? Since I didn't think about it ahead of time. So had I thought about it, I might have said, well, I would have known that answer. Again, can you get that in your head? If I'd have said -1, not -0.82. Can you get that in your head? I hope you can. If the middle was 68%, then it's missed 32%. And so since this is 50% on this side, if 30% of it, 32% of it is right there, then wouldn't that mean that's 18%? 34, thank you. What did I say? You should know this. I'm gonna scratch that. So this should be 16% out there. So then what kind of an answer should we get? Since we weren't actually here, we were over here. A little bit more, right? So I might have guessed 18%. I would have been wrong, but it's like, yeah, 20. Okay, that makes sense. You see what I'm saying? Like, we're not really learning anything new. We're just learning how to get what you already knew, plus a whole bunch of other answers that a person might want to know. Because again, if your kid comes in, are they going to have a Z-score of 1 or 2? No, it's probably going to be like 1.7 or -2.89 or something like that. And so, then it would be like, well, what's the probability of someone being born this small, and being able to talk about that? That's pretty practical. Can you do this? Let me show you one kind of cool thing. And we'll take a quick break, and I'll show you one other thing that you need to know. You cannot minimize when you are recording Zoom. Didn't know that. You do not need to know this. This is just kind of neat. Where does this come from? Again, we're pushing buttons in some calculator and it's telling us the answers, but it's entirely magic, right? We have no idea how it's doing it. That's why we paid $140 for the STEM calculator. So give us all the answers we need to figure out for the real world, right? But I just want to show you because it's kind of interesting. So it turns out that curve that we've been talking about and so forth, it actually comes from a math equation. And this math, and the reason I'm showing you this is this math equation should be significantly over your head. It's e raised to the x squared. Now you don't know what e is unless you've taken math 111 or math 111 or higher, which you shouldn't have or you wouldn't be in this class. And so some nerd figured out that equation. That's why we have a calculator that does this for us. And that's why it cost us $140 to get this, because some nerd knew a lot and spent a bunch of time to program that. That's how the world works. If somebody knows something you don't know and you need to know it, guess what? You're going to pay them so that you can have what they have. I can't fix my car. Here's my car and here's $500. You can't do it yourself. You pay someone else to. So it turns out that's what that curve is. And then in calculus 2, way past that, watch this. I teach something called an integral, which is area under the curve. And again, I just want to show you this because it's interesting. Let's see, where is that integral? If I say, what is the area? This is what this little symbol means. What is the area under that curve from 1 to -1? notice it says, hey, 68.26. Isn't that the same thing we just got? Like it took calculus 2. So at our school, that would be math 60, 65, 95, 111, 112, calc 251, calc 252, 7 math classes. And then you'd be able to get what you have without that calculator. So 140 bucks is pretty cheap relative to all that time paid, true. But that's kind of cool. And the real reason I'm showing you that, because we have a machine that does this, is just to appreciate there actually is something in those classes that does eventually come out of the clouds and become useful on occasion. And that's the kind of math I'm excited about, is stuff that actually helps people do things, allows you to make your life or somebody's life a little bit better as a result of it, build a bridge that doesn't fall down, correctly diagnose a medical problem and fix it correctly and so forth. But that's where this comes from. And so these problems we've been doing, I can answer all of them just using this. We said, what's the area under the curve above 2.1 a second ago? So the lower limit is 2.1, the upper limit is whatever, 12. Isn't that the area we just got a second ago? So that's kind of cool. Okay, let's take a whatever 5-10 minute break. If you have math questions you want to ask or something I showed you today, when we come back, I'm gonna show you the other thing on this note sheet that we didn't talk about, which is inverse normal and what that does and so forth. So. Catch up on all that.
I got the 6.2 done and the lab done with the tutor online. The only one that really knows anything on the online stuff, I need to save. The rest of them, they don't.
Those are hard questions.
So, but yeah, she's been helping me every day just about to
Cool.
figure it out.
Where is she?
She's on the online, the Zoom part of it.
Oh, got it. Okay. Yeah, she's in the online tutoring. Yeah. I should know. Sage is the one who wants help with it. Yes, over there. Back to 12 to 1, that's what I was thinking.
Yeah, no, that time, just before.
So the other option would be just to come to 30 bucks and take the things that you want to take.
I'll say it, on their side.
Okay. So this is tricky because you all have a 76 and an 80, so it's kind of. Turns out it's 80 because that's when we pass them from the book. So we're booking 80, so the question is, and notice this goes all the way. So it's just that what we're going to investigate is if they booked 80 because they didn't think everybody was going to show up for the flight, which kind of makes sense. then that would make sense because we book more than the 76 seats. So a lot of the questions around, around 76, it's 80 or so. So then, yeah, I think it's nice. So you say 80, much more than we're using. Helps you understand what's going on over there. The other one's more magic. So now I want you to literally go over here and like add all of those up, you know, and see what percent that is. Now, the empirical rule would predict this is going to be 68% or something around there, right? So does that actually happen? That's why I just wanted to kind of say, perfectly, or oh, it's a little high taxes on comments. And see. Is this the right? How do I get off this? Yeah, every time, you can always say undo, but when you're in a cell that has an equation in it, every time you click somewhere, it thinks you're trying to add that. So if you're in there, go and do. And you don't want to anymore, I will check this box, I'm just going to check. Let's say get out of that screen. So yeah, I just, will try to do this, because I'm here because. Yeah, I mean, that's right. If I'm saying deviation, yeah, but how would I do it? Like I was trying to do something last time. So one of making this too hard, not just in generic probability distribution format. We're changing up to really in this section. To do this. So you could have gotten that 380 by just taking n times 2 and move it up 380. Because this is a binomial probability distribution. This is the binomial. You know that n is 4. Well, that's the maximum. Yeah, that's what. So that's and what's the probability of all you would multiply this and you get you're going to get the same as you got. It's going to be so that'll that one. Yeah, so what you make that, you don't want to grab everything. You want to grab just the ones on the right, because the problem is that if you grab both sets, it doesn't know that you need the left ones are X and the right ones are Y. So now the only thing with that graph is notice your X's are wrong, like you want to go back to 387, 387, 388. Because you didn't select over there, it doesn't know what all those numbers except 1, 2, 3, 4, 5, 6. So how do you fix that? So you see all the horizontal axis right here? That's what it says here. So where are you?
That defines the line. This side of the shade. Tell me about. You gotta think up with another. That's just the road. That's the other. And then you get the shade, and that's the other.
I know what shade where I got a shade. Yeah, you can borrow it. I think you use it once.
I go without it.
Yeah. I don't know when they're, I know, that's what universities are like. This is my, I just have to. Yeah, I would just have it out.
That's not very clear in this case, because they both do this. That's the one that else. So it's not on this. So you're over it to 80. And now we're answering a bunch of questions around 76, because that's what we include. The idea that section 77 shall come from each other. But this probability, so that's not. Kind of look at 76 or less. 56 or less, then I'll just extra clear, right? So because it's at least one, that's one. Lots of us to have, but the answer to the question is really. But what is this part? So you have these. So because it's only 76 seats on the board, there are 75 choice, that makes it 74 should be two, 73 should. You got a whole bunch of them to add. Here, that's the other one, and then the other one.
Okay, we'll have some more time in a second. Let's get rolling.
Yeah, well, I don't say around, but it's never been more than 4 places. So if you do something that's rounded to 4 places, it's all zeros. But if it's not, then there's one, and then start with numbers.
Okay, so hopefully you feel reasonably good about, and we'll take a look at my open math in just a minute. But the second thing I want to look at is not how to go from a z-score to what percent of people or what proportion of people or what's the probability, but what if we want to go the other direction? And this is the last thing you need to understand today. What if I actually have the proportion of people or the probability of people or the percent of people? What if I have that, but I actually want to work backwards and get a z-score out of it? What would that look like? And again, that would be something like this, like this time, instead of a z-score locating us, what if I was considering, say, it's considering like, try to get into an Ivy League college, and it's like the top 2% of people make it into this Ivy League college. And so you're kind of wondering, like, what does it take? What kind of GPA do I have to have? And how much community service and how rich do my parents have to be or whatever? I want to be in the top 2% of people. Does it make sense that that is an area? That's not a z-score. This time you have the area that we were hunting for before. We had the z-score, we were trying to get an area. Now we have the area, but we'd like to know what z-score that is. So isn't the top 2%? Notice I didn't say the bottom 98%. I said the top 2%. So isn't that these people? Isn't that what their area would be? Now, if I said bottom 2%, then that would have been shaded over here, right? So to be in the top 2%, basically, there's the line right there. And that's kind of what, the line you want to hop over if you decide you want to be in the top 2%. What would that z-score be? Now, again, you should have an estimate for that based on exactly on this discussion right here. If this was a z-score of 2, then this area was 2.5%. Well, we don't need quite that much percent. We don't need 2.5%. We only need 2%. It's kind of annoying that this is a 2 and that's a 2. Probably a little overwhelmed with 2s, but that's okay. We'll leave it. So if that's 2.5%, I don't need quite that much. And so does it make sense? I might have a z-score of 2.2 or 2.3 or something like that. I don't know. How do I work backwards? Well, that's what inverse normal. What does it do? It returns the limit defining that area. In this case, we're using a z-score. On Wednesday, we'll be looking at this in a little bit broader lens, but we're looking for the z-score that would define that. Notice, interestingly, this only works though if the area is to the left. Am I doing a problem with the area to the left? No, my area is to the right. See, the problem is if I just type 2% in, how does it know whether, if I type 0.02, how does it know that I don't mean this 0.02? Do you see what I'm saying? Which 0.02 do I know? Well, it basically for that reason is saying you can't just use the percent and put it any place you want. It has to be to the area of the left. So if this is 2%, then automatically this is 98%. And unfortunately, in this case, that's actually what you have to type in there. So if you wanted the top 2%, the only thing you can type in is the area to the left of the line, not the area to the right. And so again, notice the syntax. It says area to the left, comma, mean, comma, standard deviation. So inverse normal. So how does that work? So again, second distribution. And you notice if you arrow down, there it is, inverse normal.
Is it similar to Q in the field, like the opposite?
Similar to what?
The early chapter with the P and the inverse of P, like the
Yes.
Q.
Yeah. So see how it's asking for area here? And if you type 0.02 in, it's not going to work. It has to be the area to the left. So I have to say 0.98 to get 0.02. And the mean and the standard deviation. Now, again, this is a nicer calculator than the 83. It doesn't sound like anybody in here has an 83, but this is the syntax. Notice when you say paste it in there, it indeed is area to the left, 0 for the mean, 1 for the standard deviation. And sure enough, look at that z-score, a little more than 2, just like we estimated it would be. So call it 2.05. We'll do some more examples. So this is the area left. So I typed inverse normal 0.98, 0, and 1, and it spit out 2.05. I don't care how you round this. I'm just going to call it 2.05. Now, again, you should say, oh, yeah, I got to have this over that z-score. That's unusual. It's like, yeah, you got to be unusual to get into an Ivy League college or whatever. And again, from a doctor's perspective, if you said, okay, this percent of patients, that's a very small percentage. And so I'm kind of wondering, these are the ones I'm going to have to treat really carefully or whatever, have oxygen, a bunch of medications and so forth. It'd be nice if somebody came in the door and I could identify whether they're in that group or not. And this is basically saying if they have that for a z-score or more, then they're in that group. It's not, that's in a sense, it's almost as a better question to ask. It's almost a more natural question. This group, everybody's good, not worried about you. This group, high cholesterol, top 2% of highest cholesterol, kind of worried about these people. So they know the mean and the standard deviation for cholesterol, and then I come in, take a blood test on me, pop out a Z-score, and I get 2.2. Oh, look, you're over that, so that's you. Now there's like a treatment that they do for those people. So now this is the line. If they have a Z-score less than that, oh, get over here with all these people, you're fine, don't worry about you. If your Z-score is over this, oh, you're in bad shape. You see, that's a pretty natural question to ask. Let's do another example. You try this yourself. Thank you. What about the bottom? Say, what about the bottom the bottom 12%? Find the Z-score. Now I'd like to, before you kind of take off in that, I'd like to show you how the My Open Math homework questions are worded, just so you kind of understand this. They're going to ask it this way. They're going to say the probability that Z is less than some number if the area or the percent is 12. Yeah, it's a C. So they're basically saying Z needs to be less than what? Well, isn't that the way these questions are worded earlier? Like I said, Z is greater than 2.1. So now it's saying, well, we don't know what that is. So rather than put a number there, it's like some letter. Notice I said bottom 12%. That's why I said Z is less than C. Up here, because it's top 2%, it would have been the probability that Z is greater than some C, because that's what top would be indicating, is above that. So again, that could look confusing in My Open Math, but not if you understand what it's asking. So what Z-score would represent the bottom 12%? Again, you should draw a picture of this, just so that you kind of say, I have a feel for what that's looking like. You should say, okay, well, there's 12%. And then of course the question is, what's that location right there? I can now see it's negative, right? You better get a negative Z-score for this. That's clear now. I didn't know that before. So I know the percent or the proportion or the probability. So that's why I'm using inverse normal. Inverse normal says the area has got to be left of the mark. Hey, my area is left of the mark. That means I can just use it this time. You tracking with that? That's how it tells the difference between the top 12% and the bottom 12%. When we use the top 2%, we couldn't put in 0.02. We had to put what was left of it. So we had to use a totally different number. Whereas here, it was the bottom, and that's what this button, if you will, is designed to do, is answer when the area is to the left. Hey, that's what we're after. Oh, I don't have to change anything then. If I put that in, I can already write it in here. This is going to be a Z-score that's negative. And by the way, as I said before, if this was 16%, then this would be a Z-score of -2. I'm sorry, -1. And we're even less than that. So I already know this is -1 point something. Just because I'm thinking, because I'm reasoning, I'm wondering. I know this is -1 point something. I just don't know what it is. Jade, didn't you have a question?
Yeah, I'm wondering like how you look at that, you just know that it would be, because like when I look at the chart, it looks like it would be -12, but it's +0.12, so I'm wondering how you are going to go to the left side of that.
Yeah, good question. In other words, it's over there on the left, but that doesn't mean the area itself is a negative percentage. It's not -12%. So that's a good question. The only thing that's negative is the z-score that goes with it. So that 12 is still positive.
Like when you're drawing it, how do you know to look that it's already on the left side if it just says 0.12? How do you know?
You wouldn't. I'd have to say bottom or something like that. You'd have to say bottom or top or less than or greater than or something. There has to be something else. I can't just say 12% because you don't know where the 12% is. There is such a thing as a middle 12%.
If it's greater than, that means bottom.
Yeah, so if it's greater than, it means top because you're higher than that number. If you're less than, if your z-score is less than a certain number, then that means you're left of that, left, and therefore bottom. So if I say second inverse normal, I get to say 0.12 this time, everything else stays the same. And it says, yeah, sure enough, that's -1. And now I know the rest of it, 0.17, -1.17, -1.2, doesn't matter how you round that. So there's my C, if you will. So I could say the z-score is actually less than -1.7. So that's kind of my C. Again, I think throwing C in there makes it a little confusing. I wish they would just said find the z-score that defines that. Find Z, that's what I said originally. Find the z-score, -1.7, I found it. I'm sorry, -1.17, it's -1.2. I got excited. So do your best to be thinking about this, like gauge it against the empirical rule that you already have some understanding of. That's why I was able to know this was around -1 before I even pushed any buttons. Now, I want to give you more of a chance to think about this a little bit. I want to do one more example, but I want you to understand, armed with these two pieces of info, just make a note to yourself, because the homework assignment, I put 7.1 and 7.2 together because they're kind of the same topic, but you're really ready for questions 1 to 13 now. If you try to do question 14, 15, 16, that's actually 7.2 stuff that we'll talk about on Wednesday. It's not a huge jump between what we're talking about right now. But notice every time here, it's always about just the z-score. Whereas as I mentioned, the next set of questions is just going to be a little more broad. Like I just come in and my baby is born at 6 pounds. And then they just tell me what % of kids are born at 6 pounds or less. So now the 6 is not a z-score, it's just my kid's weight. And so I have to turn it into a z-score from the mean and the standard deviation. So here we're just working with z-score directly. But we've played in the last section with how to get a z-score and the formula for that. So it's not going to require any new knowledge, but it's just making the question a little bit more realistic. Because as I said, my patient comes in with a z-score of 7. Well, how do you know what the z-score of 7 is unless you made a calculation, right? I mean, you don't just know that. So that's all 7.2 is going to add. But my advice would be go get 1 to 13 done effectively after today. Go ahead, Blake.
It has this one,
Thursday. So yeah, let's briefly. Let me just-
and I presume chapter 7 will also be on this one.
Yep. So it's basically, it says 5, 6, and 7, but chapter 5 was probability. We did it for like 1 day, super quickly, half a day actually. There won't be any chapter 5 questions. Chapter 6 is this set of formulas, these two probability distributions, and chapter 7 is what we're doing right now. And notice that's the end of this note sheet. There's nothing else on it. So it's really just this stuff, mainly these two things. So you're basically almost there. So plan tomorrow is to review for the test next door. and then talk about 7 points. So in a sense, hopefully after tomorrow, you feel reasonably good about everything except for this. And it won't take all day for me to show you 7.2. So we'll have time, you know, another whatever, half an hour or 45 minutes or something after the end of this discussion to kind of also answer review questions that you have and so forth. Maybe there'll be some things if you start working on the review over the next couple of days, maybe there'll be a couple of things you're like, I don't really get that. And then we'll still have time to talk about that before Thursday's test. So we'll take that next door. And then we'll be done with second test. So let me ask just one more example question. Trying to think how these things are worded. So what if we're talking about a strong majority of the population of people, kind of the upper 69% of the population? Again, we could be talking about how many cars they've owned in their life, the top 69% of sort of richest people that have owned the most cars, smartest people. Doesn't have to be something positive. It could be the people with the, you know, highest glucose numbers. That's not a good health number, is a high glucose number. So the upper 69% of people that have kind of the highest glucose, maybe these are the people we decide we're going to worry about. So again, in my open math, because of the word upper, it's going to say the probability that the z-score is bigger than some number. What's that number right there? Can you find out what that number is? Can you draw a picture of that? Do you have a sense of what that's asking? Do you see this as an inverse normal problem because you know that percentage, but you don't know the z? Normal CDF is when you knew the z but didn't know the percentage. Inverse normal is when you know the percentage, but you don't know the z-score. If you got this, you should know that's wrong. Why should you know that's wrong? Again, in my opinion, it's mainly because of drawing pictures. If I said upper 69%, and again, you hopefully at least 3/4 of you already know that I typed the wrong thing in from the start here, but again, because I'm more concerned about you learning how to think, if I said upper 69%, you should be able to draw that. And because zero's in the middle, you should say to yourself, hey, 50% is right there. The right half of that's 50%. So if you're going to get the upper 69%, then wouldn't you have to be over here somewhere? So could you have a z-score of positive 0.5 and be right there? You see what I'm saying? You should know that this is going to be a negative z-score from the picture. I need to physically draw that, and I know this class pretty well. I think you should too, for at least for a while. So clearly that should be a negative z-score. So it's like, don't do that and not know it's wrong. What did I do wrong? Somebody tell us. Yeah. Unfortunately, the only thing you could type in is the area to the left. This problem, unfortunately, was talking about the area to the right. So what did I actually need to type in? Yeah, the area to the left as a consequence of 0.69, again, upper 69%, the top area to the left is 0.31. So what I should have typed is inverse normal 0.31.
So upper always refers to the right.
Yeah, and there's different language that could be used in the assignment. Like 6.2's assignment, you're gonna have to read that. I just use upper and lower kind of every time, because that's kind of typically what we do in English. We say, oh, that person's in the top 10% of best triathletes there, or this person has the lowest times of any other racer. They're in like the lowest 1% of best times that people could possibly get. And so then if I type 0.31 in, and indeed I do get a negative, and by the way, is that a coincidence that those are the exact same answers? Just one was negative, one was positive. The answer is no, because it's symmetrical. When I typed 0.69 in, I actually got the area that was in the same location, except for on the other side over here. Basically the 69, it thought I meant over there. So it's not a coincidence. Those are basically the same numerical answer, but just not the right sign. Yeah, would you agree that's kind of a hassle, like to keep that straight? The TI 84 plus, look what it lets you do. So to charge more money, to constantly improve, I'm not sure what their motivations were, but this is the TI 84 plus CE. The only reason I bought this is because it has a backlit screen and it's easier to read. Notice it actually lets you type where the tail is. So I could actually go in here and type 0.69 as long as I just made a note that that's a right side tail, like that area is on the right side, and it'll still give me that negative 0.49 answer. So that's kind of cool, if you will, that they added that in. Then I don't have to think. So if in a sense, 3 years from now when I teach this class and all the calculators are like this and better, maybe that note sheet won't have to include this kind of little note. But again, if you say, oh, that's stupid, man, this should include this. Well, if it wasn't for this calculator, you'd be having to do Calc 2 to be able to get these answers. So it's pretty cool that we have access to that from a machine that's relatively inexpensive. That's kind of neat. Okay, let's take just a quick look